Hello students, today we will study total differentials and total derivatives. In the previous class, we have studied partial derivatives of two variable functions, that is del del x of f and del del y of f. These give the small change in the function with respect to any one variable, keeping the other constant. Okay, so when we require total change in z, where there are small changes in both x and y, then this purpose is served by total differential or total differential coefficient of z is denoted by dz or df, and dz is equal to del del x of f dx plus del del y of f dy. Now we will prove it that this dz was equal to that. So let delta z be a small increment in z corresponding to small increments delta x comma delta y in x and y respectively. Then we have z plus delta z is equal to f of x plus delta x comma y plus delta y. Therefore, z plus delta z minus z is simply delta z, and it is equal to f of x plus delta x comma y plus delta y minus fxy, or delta z is equal to f of x plus delta x comma y plus delta y minus of fx comma y plus delta y plus f of x y plus delta y minus fxy. So what I am doing here, just adding and subtracting this. Okay, so I think there will be no change in the right hand side. Okay, this is just for arriving at the desired result. So delta z is equal to, now what we are doing, we are separating these two terms and last two terms. So this minus this, and then simultaneously we are multiplying and dividing by delta x to this term, and similarly multiplying and dividing by delta y to this term. When delta x and delta y tends to 0, okay, we have dz is equal to limit delta x tends to 0, delta y tends to 0 to the whole term. Okay, then again just separating these two terms and taking limits on them separately, we get this step. Then dz is equal to, here what I am doing, just taking the limit delta x tends to 0 inside and delta y tends to 0 outside. Then this is f of x plus delta x comma y plus delta y minus f of x comma y plus delta y upon delta x into limit delta x tends to 0 delta x. And similarly the second term, you can see. Now this, by the definition of derivative, this inside term is del del x of f of x comma y plus delta y, and this term is del del y of f of xy. Okay, you can observe here, only there is a change in y and x is kept constant. Only there is a change in x and y remaining the same. Okay, the next step, dz is equal to limit delta y tending to 0 inside what I just told, this is into dx plus delta x tends to 0 into this into dy. So dz is equal to del del x of fxy dx plus del del y of fxy dy. Okay, so this limit is equal to this one if fxy is a continuous function of y. Find the total derivative of fxy is equal to 4x square plus 3y square. So we will directly total differential of. So we will directly use the definition of total differential, and this is df is equal to this one. So we need only to find del del x of f and del del y of f. So this is your f, right? So if we do it, we get del del x of f as 8x and del del y of f as 6y. This is the answer. And now coming to total derivatives. If z is a function of two variables x and y not independent, and x comma y are themselves functions of some other variable, say t, that is x is equal to phi t and y equal to psi t, where t is independent variable. Therefore z is a composite function of one variable t. In that case, the ddt of z is equal to del del x of f into dx upon dt plus del del y of f into dy upon dt. And it is known as the total derivative of z with respect to t. Now we will prove it. Let delta t be a small increment in t, and let delta x, delta y and delta z be corresponding increments in x, y and z respectively. Then ddt of z is equal to limit delta t tends to 0 f of x plus delta x comma y plus delta y minus fxy upon delta t. Then limit delta t tends to 0. Here again what I am doing, to the right hand side I am just adding this quantity fx comma y plus delta y and subtracting fx y plus delta y divided by delta t as it is. So after that, in the next step, limit delta t tends to 0, this first two terms, and just multiply and divide by delta x, delta x, delta x, and delta t was earlier, plus similar thing is done with the second term, delta y, multiplying and divided by delta t. So as delta t tends to 0, delta x and delta y also tends to 0. Therefore we have ddt of z is equal to limit delta y tending to 0 and limit delta x tends to 0 f of x plus delta x comma y plus delta y minus fxy plus delta y upon delta x into limit delta t tends to 0 dx upon delta x upon delta t, and similar thing is done with the second term. Okay. So therefore we get limit delta y tends to 0. This term is del del x of f x y plus delta y, and this term again is del del y of f x y, and therefore limit delta y tending to 0, del del x of this into dx upon dt plus del del y of f x y into dy upon dt. And as we have done earlier, this if fx y plus delta y, del del x of fx comma y plus delta y is a continuous function of y, then the limit delta y tending to 0, this quantity simply becomes del del x of fxy. So therefore we have del del t ddt of z is equal to del del x of f dx upon dt plus del del y of f dy upon dt, which is the proof to that formula. Now some useful reduction those can be made. If we put in the previous formula t is equal to x, in that case y becomes a function of x. Okay, then from 1 we can have t dx of z is equal to del del x of f plus del del y of f into dy upon dx, because dx upon dx is equal to 1. So here 1, therefore this is the formula in that case. Now suppose x and y are related by some implicit function of the form fxy equal to c, where c is some constant. Here c could be 0 many times. So therefore df of this is df of del del x of f dx plus del del y of f dy is equal to 0. That is this constant derivative df, constant derivative of this is equal, differential of this is equal to 0. So therefore we are left with this left hand side, and again if y is a function of x, then we know from the previous point that this becomes del del x of f plus del del y of f into dy upon dx, that is equal to 0, and therefore this gives me dy upon dx is equal to minus fx upon fy. This is important result in case of implicit functions. Now I have one example based on this. If x raised to power 4, 3x square y square minus y raised to power 4 plus 2x minus 3y equal to 5, then find dy upon dx. Okay. So in this case, let f is equal to this one, minus 5 equal to 0. So we can see that it is an implicit function. Therefore, in order to find dy upon dx, we will directly use the relation this, that dy upon dx is equal to minus fx upon fy, and which is equal to this one. Next is some more exercises. If z is equal to 2x square plus 3xy plus y square and x is equal to this t cube plus 2t minus 1 and y equal to t square plus t minus 3, then find dz upon dt. So in this case, you can use this formula dz upon dt equal to del del x of f. So in short, it is noted by fx dx upon dt, then fy dy upon dt. So we can find it. Second is the dx of u of the function. Find the dx of u of the function. U is equal to this and y equal to 1 upon x. So you can see that y is a function of x. In that case, we will use this formula. Dx of u equal to del x of u plus del y of u into dy upon dx here. So you try out these questions and some more questions based on these questions from the book prescribed to you. Thank you very much.